Good afternoon. Thanks for coming. So today I'm going to talk about democratizing AI. So I was asked to start with my personal journey. So I thought I'd start at the beginning. I was born in London, and I did my elementary school in London. And then I moved to Nigeria and did middle school and high school. And then I did undergraduate and graduate school at Michigan. So in the first 20 years of my life, I lived on 3 continents. And that gave me broad exposure to people, different people, culture, and ideas, and made the idea of trying new things, expanding into new areas, seem kind of natural, and gave me a kind of pioneering spirit. But I didn't actually do any actual pioneering work until I became a Stanford professor. And whenever you pioneering in the academic world, it's all about doing things before it becomes the popular thing to do, and sometimes you're doing things that people think are a bad idea. That was certainly the case for the work that we did in the multi-core processor space before it was popular, and most people were working on single processors and making them faster, and we said that eventually you're going to run out of steam on a single processor, and you need to think about how you put multiple processors on a chip and how to do that efficiently. And we did that, and we showed that it was a good idea, and we founded a company based on that. It was called Afara. It got acquired by another company called SambaNova Systems. And then I went back to the university and started thinking about how to develop software to make multi-core microprocessors more useful. So we came up with the idea of domain-specific languages, which was an idea that, of course, people are using all the time to do machine learning. And we showed that early prototypes of what you could do with domain-specific languages and AI before AI blew up, right? So, in the early 2000s, we showed that you could apply multi-core ideas to AI and get much better, much higher performance and much more efficient processing. And that leads to the work that we're doing today about new ways of developing hardware and software that will make AI technology much more accessible, and we're doing that with a couple of startups called SambaNova and Migo. So, as examples of how technology can change, become democratized, can change human history, we have the printing press. So the invention of the printing press, of course, changed the way that knowledge was disseminated, because you were able to use mechanical movable type to generate books much more efficiently and much more cheaply, and you took it out of the realm of the high priests. The same thing occurred for time and longitude. To provide safe ocean navigation, you need to be able to figure out both latitude and longitude. But before the advent of the chronometer and the sextant, you weren't able to effectively calculate longitude. And so what happened was that only the Venetians, who controlled the trade around the Mediterranean, were able to determine world trade. However, once you had time and longitude, now you could navigate the oceans and you could open up trade across a much wider area. And the last example is the automotive industry, which Henry Ford revolutionized with the assembly line, faster production, cheaper production, and which made cars and automobiles much more widely available. And so you think about printing press, right? Well, this is all about creating a freedom, democratization of knowledge, and creating a freedom of ideas. Time and longitude, democratization was unleashing of markets, making trade more accessible, and the automotive democratization allowed movement of people and cheaper automobiles. Now, AI, of course, has the potential for much greater societal impact than any of these technologies, and the key thing is making the elements of AI accessible to a much wider set of people than traditionally has been the case. So AI, of course, is ripe for democratization because there are lots of uses for AI, and we've already heard about some of them already, but you can think of any area of society: health, education, transportation, communication, they all will be disrupted by AI, so there's lots of potential demand. But of course, we need to make sure that as AI gets used, it gets used and developed, and the models get developed by a diverse range of people so that we don't get the biased situation that we have currently in some of these applications. Now, the supply side is what is missing to create the democratization, and the tools are starting to become available, but they aren't at the level at which that makes it accessible to most of the people. So if you look at what the situation is today, you have a situation where, for many tasks, these tasks that were thought to be difficult tasks, such as speech recognition and object recognition, the AI-powered algorithms are able to reach human-level accuracy. This is just an example showing speech recognition accuracy over time. And however, if you look at the people who are able to develop develop these sorts of systems, they're in the hands of the few. The large companies that have both the data, the computation, and the talent to develop these sorts of algorithms. And of course, they've used this capability to develop them. These companies have used these systems to become the most valuable companies in the world: Google, Amazon, at Facebook, at Apple, and the like. And so the question is, how do we enable more people to have access to these sorts of technologies? Well, if you look at the key ways that these companies have been able to develop these applications, it's by you taking massive amounts of data and building more and more complex models that have higher accuracy. And the way that you enable this, of course, is with more powerful compute. And so what has to happen to make these technologies more accessible and more available is that we need a revolution and disruption in both the hardware that powers AI and the software that develops the algorithms. So what does this disruption look like in the hardware? Let's first look at the hardware. So if you look at the process of developing these AI or machine learning models, right? So most of AI, of course, is actually machine learning. The AI, as Greg said, is the PowerPoint version. You see that the training is done by specialized ASICs like TPUs or more general accelerators like GPUs, and that inference, which has to happen with very low latency as the request comes in. You want to evaluate the model. So training is building the model, and inference is evaluating the model, and that's typically done with low-power ASICs or CPUs. And what we believe is that inference and training have to be merged, and the reason that you want to do this is because you want to be able to use much less complex, smaller models, and the only way for that to work is to be able to train these models continuously, right? And so if you need to train continuously, then you need to have the ability to do both inference and training on the same sort of hardware. The other benefit that you get by doing this is that you get to fine-tune your model to take advantage of the environment in which you are trying to make predictions. So how do you come up with a platform that provides the capabilities for both inference and training, given the challenges of the environment that we currently see ourselves in, right? So Moore's law, of course, which has powered the semiconductor and the computer industry for the last 50 years, is basically slowing down, right? It may be not quite dead yet, but it's on its last legs, right, in terms of the improvements that we have seen over the years. However, more importantly, there's this other thing called Dennard scaling, which says the power efficiencies you get from future process improvements have basically ended, right? So now we're power constrained, and that means everything has to be done more efficiently. So if you look at the current landscape of computation. On the x-axis, you see flexibility, which is sort of how easy it is to develop software for your particular piece of hardware. And on the y-axis, you see performance, right? And so what you see is that CPUs, of course, are the most flexible computing device, but they also are the least performant. And then GPUs, of course, provide more performance but less flexibility. And then specialized ASICs, especially ASICs that are focused on a particular machine learning algorithm like dense matrix multiply, which, of course, there's a lot of things you can do with dense matrix multiply, but it won't do everything. Like the TPU, they get much higher performance, but of course, they're not very flexible. So what we need to do is we want to break out of this curve defined by traditional architectures and provide a new paradigm for doing hardware compute that we call reconfigurable data flow. And reconfigurable data flow is a ground-up reimagining of how to do compute based on focusing on what machine learning algorithms need, right? And so if you look at what reconfigurable data flow is, it is a sea of computation and memory closely coupled together by a programmable network. And the key to that programmable network is you can program the data flow between the different compute and memory elements in a way that matches the needs of the application that you're trying to run. So as an example, here is a image processing, object recognition pipeline, from a neural network benchmark called AlexNet, just a piece of it. And you see, multiple components which are connected together by the data that flows between them, right? So you've got convolution, followed by pooling, followed by batch norm. And the way that you would map that to a reconfigurable data flow architecture would be to map the different kernels onto the compute and memory units, and the data flow would be provided by the underlying connectivity between these units, and it would completely match the flow of data from that you would see in the neural network would be matched on the chip. And so what you would get is very efficient data flow communication and very efficient use of the utilization of the compute and memory, which would lead to very high performance and very high efficiency. The other benefit, of course, is if the algorithm changed, you just reconfigure to match the data flows in your new algorithm. So the other part of the disruption, right, so we disrupted hardware with this new paradigm for computation called reconfigurable data flow. The other piece is the software, right? And the software is also changing, and it's changing it's what we call software 2.0, right? And so if you think about conventional software development that we're calling software 1.0, it's focused on algorithms, and it's focused on instruction flow, right? So you have a problem, you find some domain expert who knows about that area, and they write a lot of C code, right? And it requires you to decompose the problem based on your domain knowledge, and then come up with algorithms for each of these different pieces, and then compose those algorithms into a system. Contrast that with software 2.0, which is data-focused and data flow-focused, where the developer curates the data, comes up with training data, and there are new ways of coming up with training data that don't require you to come up with individual examples for each of the elements of your training data set. But the point is, it's all about the data, and the data is used to train models, and the training process is an optimization process that gives you a network, right? And then the network then can be used to solve your problem. And so what you find is that it's often much easier to apply the software 2.0 approach compared to the conventional approach, in that it's cheaper and easier to come up with a model that you train based on data than it is to go the conventional route of developing algorithms and composing them together. The example shown here is Google Translation, right? So Google shrunk their language translation from 500,000 lines of code, which was conventional C code, to 500 lines of data flow. So it's data flow, and of course, as I said, you want a data flow. If you've got a data flow problem, you want a data flow computer to solve that problem, and that's what you get with reconfigurable data flow. And it's not just for the high-end problems of language translation, image recognition that this software 2.0 approach works. It also works for classical problems. Turns out that many classical problems, from data cleaning to networking to databases, have a bunch of heuristics in them. And the algorithm, much of the problems can't be solved without heuristics because they're NP hard. And so what you find is that you're better off replacing those heuristics with models based on data, because you both get higher accuracy, better performance. You get the better, your software performs better in terms of the goal that you're trying to achieve, but also the software works better, and it has more predictable memory behavior, and all around, it's easier to deploy these sorts of solutions. So it turns out that reconfigurable data flow architecture and software 2.0 form this virtuous cycle, right? So reconfigurable data flow architecture is going to give you efficiency in terms of executing these sorts of applications, and it's also going to enable you to do things that you couldn't do before if you were running these applications on conventional hardware. So it unlocks a whole new genre of applications by having this efficiency, and it enables you to create. It creates a platform that can be used for developing a whole new set of applications based on AI. And software 2.0 then, of course, is, as I said, the application development is data flow. You typically develop these applications using these high-level frameworks like PyTorch and TensorFlow, which were, of course, developed in Python. And, in fact, as I said, come out of some of the ideas that we developed about 10 years ago about using these specific domain-specific languages to develop machine learning applications. And once you've got data flow, then, as I said, the best way to execute data flow is with a reconfigurable data flow architecture. And so as an example of sort of how you might use this technology, this is a collaboration with a colleague of mine at Stanford, a guy named Vijay Pandey, who's a professor of bioengineering, and he is also famous for doing a distributed computing project called Folding at Home. So he's very interested in how proteins fold, folding from left to right here. Turns out, I don't know much about biology. I'll have to ask Greg for some primers on this. But apparently, proteins don't just fold one way. There are multiple trajectories that proteins take to fold. And it turns out you can analyze these trajectories with a type of machine learning model called a Markov state model. And so it turns out that Pandey's group decided to write some code to analyze these Markov state models, and they wrote it in Python. But it was far too slow. So they got a CS undergrad to code up the Python and make it much faster. So that CS undergrad said, I know how to do that. I'm going to write it in C++, which is a much lower level language than Python, and I'm going to throw in a little x86 assembly language for good measure so that I can get much more performance. And they sped up that Python by 1,500 times. And then, of course, they got hired by Facebook or Google or so on. And they left the group, and then Vijay's group of biologists didn't know what to do with the code. And so we came along, we said, what you want is a domain-specific language that allows you to express things at much higher level, and not only can you get the performance that you get, you can get better performance on the C sorts of implementations, but you can speed things up by another factor of 3 or 4 by using domain-specific languages. And this is even before we get to the reconfigurable Dataflow architecture approach that I just described. So what is the impact of this? The impact is to enable the other 99% of people to use AI technology and to create applications that are more widely applicable to more of the world. So if you think about what SambaNova is doing, we are in fact developing this reconfigurable Dataflow architecture and technology around software 2.0. So both the hardware and software that is required for this AI democratization. And then there's another company I'm involved in called Migo, which is using this technology to make AI technology accessible to the wider world. So Migo is focused on the 2 billion mobile users in emerging markets without credit histories, and some of them without even bank accounts. And what it is a platform for consumer enterprises to offer cash loans and point-of-sale credit. And the way that we're able to do that is by aggregating data across all of these consumer enterprise partners to build AI models that can be used to underwrite the loans. So you didn't have to consult a FICO store. You could build a model that would tell you whether someone was a good risk or not. And so it turns out the majority of the borrowers are small merchants, delivering last mile retail. So it's having it really is having a direct impact to these sorts of retailers in both Nigeria and also in Brazil. So with that, thank you.